Right now, hiding behind the drywall in, in millions of garages across the country,
Hmm.
there's this piece of metal quietly baking itself to the point of melting. And the plastic insulation around the wires is, slowly turning brittle.
Yeah, the connections are scorching.
Right. And the craziest part is that the people sleeping just a few rooms away have absolutely no idea. I mean, they walk past this gray metal box every single day, completely oblivious to the fact that their home central nervous system is on the verge of catastrophic failure.
It really is like the ultimate blind spot in modern home ownership. I mean, we demand a staggering amount of energy from our houses today, way more than they were ever originally designed to handle.
Yeah.
But we treat the electrical infrastructure like plumbing, We just
Mhm.
assume if nothing is leaking, well, everything is fine.
Exactly. Which brings us to the mission for today's deep dive.
Yeah.
We are tearing open that gray metal box to figure out what is actually happening behind the drywall. We're drawing heavily from a comprehensive guide on electrical panel upgrades by Burleson A.T. Electric, authored by John Constantine.
Right, along with several other deep dives into modern power demands.
Yeah, we're looking at this incredibly tense clash between the rapidly evolving technology we buy for our homes and the static aging infrastructure we plug it into.
Oh.
But before we get to the terrifying melting panels, let's establish a baseline. What is this box actually doing?
So the easiest way to visualize your electrical panel is to think of it as a massive traffic distribution hub. The local utility company sends a massive high-capacity feed of raw power directly to your house.
Okay.
If you plugged your television directly into that main feed, it would instantly explode.
Oh, wow.
Yeah, so the panel's primary job is to take that massive inbound river of power and divide it up into safe, manageable streams, the individual circuits that run to your kitchen, your bedrooms, your air conditioning system.
And each of those individual circuits is guarded by a circuit breaker.
Right.
I think most people know what a breaker looks like, the little black switch you flip when you blow a fuse.
Right.
But how does it actually know when to shut off? Is there a tiny computer in there monitoring the power, or what?
No, actually, and the mechanical simplicity of it is brilliant. Inside a standard breaker, there is what's called a bimetallic strip. It's literally two different types of metal fused together.
Okay, two metals.
Yeah, and as electricity flows through that strip, it naturally generates a tiny bit of heat. If your appliances start pulling too much power, say you plug in a heavy space heater and a microwave on the same circuit, the current increases and that strip gets hotter.
Let me guess. Because they're two different metals, they react to that heat differently.
You nailed it. One metal expands faster than the other, so as it heats up, the strip physically bends.
Oh, I see.
Yeah, if the circuit gets overloaded, the strip bends so far that it triggers a spring-loaded latch, which physically snaps the switch into the off position and breaks the electrical connection.
That's crazy.
It literally sacrifices the connection to stop the wire in your wall from turning into a toaster filament.
That is surprisingly elegant. But John Constantine's guide points out a massive bottleneck happening in millions of homes. I mean, we have older houses operating on a 60-amp or maybe a 100-amp main service panel.
Right.
Because back in the 1970s, you had a refrigerator, some lamps, a tube television. The demand was pretty low. But today, the modern standard is a 200-amp minimum.
Yeah, think about the physics of what happens when you try to run a 200-amp lifestyle on a 60-amp panel. Let's talk about volts and amps really quickly to make sense of this.
Sure.
Voltage is the water pressure pushing through a pipe. Amperage is the actual volume of water flowing through.
Okay, got it.
So if you try to force a massive volume of water, like your high-efficiency HVAC, electric water heater, and a couple of air fryers, through a tiny 60-amp pipe, the friction becomes immense.
It's like trying to force 10 lanes of rush hour highway traffic onto a single-lane dirt road. The traffic might eventually get through, but the congestion is horrific.
Exactly. And in an electrical system, that congestion, that friction, manifests entirely as heat. When you operate a modern smart home on an undersized panel, you are forcing those bimetallic strips inside the breakers to operate just below their tripping threshold all day, every day.
Oh, man.
The entire box is essentially running a low-grade fever. Over time, that chronic heat degrades the internal springs, it degrades the copper wiring, and most dangerously, it degrades the main bus bar.
Wait, the bus bar is the heavy metal spine inside the panel that all the breakers snap into.
Right, exactly. It distributes the main power to every breaker. When chronic heat degrades the connection points on that bus bar, you get even more resistance.
Which creates even more heat.
Right, it becomes a vicious cycle that literally bakes the plastic insulation off the wires inside your walls.
Exposing live current directly to dry wooden studs. Which brings us to the most alarming part of this deep dive. Because while chronic heat will eventually degrade any overloaded panel, Constantine's guide highlights a historical legacy where this overheating wasn't just a byproduct of old age.
No, it was a built-in feature.
Yeah, which is wild.
We have to look back at the post-World War II housing boom. Developers were throwing up suburbs at an unprecedented rate, and they needed cheap, mass-manufactured electrical components to keep up with construction.
Just churning them out.
Exactly. And two major brands dominated this era: Federal Pacific Electric, commonly known as FPE, and Zinsco. Millions of these panels were installed across the country.
Yeah, I started calling them the danger brands in my notes. Because decades later, field data and safety testing proved these panels aren't just worn out, they have catastrophic systemic design flaws.
Let's start with Federal Pacific Electric. Remember that elegant bimetallic strip we just talked about?
The one that is supposed to bend and trip the breaker when things get too hot.
Right. Well, FPE breakers have a well-documented, horrifying tendency to simply jam. The mechanism fails to disengage.
So a dead short happens. Maybe a wire gets chewed by a mouse or an appliance malfunctions.
Yeah.
And instead of shutting off the power, the FPE breaker just holds the gate open.
Exactly. The circuit remains completely live. The wire in your wall pulls massive, unregulated amounts of power.
Oh my God.
It turns glowing red hot, acting exactly like the heating element in your oven, and ignites the drywall.
And the Zinsco panels have a completely different but equally terrifying flaw involving the bus bar itself.
Yes, Zinsco's flaw is a masterclass in why material science matters. They used a specific combination of aluminum alloys and clip designs that were highly prone to oxidation.
And oxidation creates immediate resistance, right?
Exactly. So where the breaker clips onto the bus bar, it starts generating extreme localized heat. The heat gets so intense it creates microscopic electrical arcing.
Like tiny lightning bolts inside the panel.
Yeah, miniature lightning bolts that literally act like a blowtorch. The heat melts the metal of the breaker directly into the aluminum of the bus bar. They arc weld themselves together.
So the breaker is physically fused to the panel. It can never be removed.
Right, and worse, because the entire casing is melted solid, the internal tripping mechanism is utterly destroyed.
Oh, wow.
Yeah, if a massive power surge hits that Zinsco breaker, it cannot physically cut the power. It just lets the surge pass right through into your house.
Okay, stop right there because this is where I was practically yelling at my notes. I mean, if FPE and Zinsco panels were installed in literally millions of homes, how is it possible people are just living with them today?
It's crazy, I know.
If there's a piece of metal arc welding itself inside my wall, shouldn't my house be ringing alarm bells?
Well, these are the ultimate silent threats. An electrical panel has no check engine light and everything is hidden behind a metal door.
Right.
It looks perfectly fine on the outside until the exact second it violently fails. But the guide emphasizes that your house actually does try to communicate with you, provided you know how to read the symptoms.
See, I always assumed that if my lights dimmed a little when the air conditioning kicked on, it just meant the power company was experiencing a slight dip.
Huh?
Are you telling me that's actually my house crying for help?
A very subtle momentary flicker is normal when a massive motor starts up. But noticeable, consistent dimming is a symptom of severe voltage drop.
Okay.
When your AC compressor cycles on, it demands a massive sudden surge of amperage to overcome inertia and spin the motor.
And if the panel can't handle it?
If your 60 amp or 100 amp panel doesn't have the overall capacity to feed that motor, the AC essentially siphons power away from your lighting circuits.
Wow.
The lights dim because they are literally being starved of voltage. Your panel is failing to balance the load.
So constant dimming is a capacity warning.
Yeah.
What about frequent breaker trips? Because I feel like everyone has that one breaker in their house that is just, sensitive.
Yeah, well, breakers are not meant to be sensitive. They're meant to be absolute limits.
Oh, really?
Yeah, if you have to walk out to the garage every time you run the vacuum and the microwave simultaneously, you don't have a sensitive breaker. You have a system screaming about capacity failure.
It's just too much demand.
Exactly. The demand is consistently outstripping the safe supply. And resetting the breaker over and over is just putting immense wear on that bimetallic strip we talked about.
And then there are the physical sensory warnings. Constantine mentions that if you walk past the breaker box and smell something acrid or catch a whiff of burning plastic, you don't call an electrician next week. You treat it as an active emergency.
Oh, absolutely. Electricity should flow silently, invisibly, and without odor. That burning smell is the literal off-gassing of melting wire insulation or plastic breaker casings.
Wow.
It means the connection is actively superheating. Similarly, if you place your hand flat against the metal face of your panel and it feels warm to the touch, you have a massive friction problem inside.
The guide also warns about rust and physical corrosion. I mean, I understand rust destroys metal, but how does moisture in a garage panel translate to an electrical fire?
Think of corrosion on a wire connection like a severe kink in a high-pressure fire hose. Electricity wants a smooth, uninhibited path. Rust and oxidation act as a physical barrier. The electrical current still has to get through, so it forces its way past the corrosion, which requires more energy and creates violent friction.
And friction means heat.
Right. That friction generates immense heat at the connection point, which then bakes the breakers and throws off their mechanical calibration.
All right, let's say someone is listening to this. They walk to their garage and they see an old Zinsco logo or a rusted out 60 amp box. The physical dangers are clear. But what fascinated me about the source material is that even if a homeowner says, you know, I like living dangerously, I'm just going to roll the dice, outside economic forces are going to back them into a corner anyway.
Yeah, this is where home maintenance intersects with the broader economy. An electrical panel isn't just a safety device, it is a massive financial lever.
Right.
And the first entity to pull that lever will be your homeowner's insurance company.
I have to admit, reading the potential cost of an upgrade, often $3,000 to $5,000 for a full heavy up to 200 amps, it made me wince. I mean, if an actuary is going to force me to drop that kind of money on an ugly metal box that doesn't even make my house look prettier, I'm going to be furious.
I get that.
Give me the silver lining here.
Well, the silver lining is that the ugly metal box dictates the insurability and value of your entire asset.
Right.
Insurance carriers employ actuaries who calculate risk down to a microscopic level. They have decades of data on the statistical fire risks of 60 amp service, obsolete fuse boxes, and FPE panels. So when you buy a house or renew a policy, carriers now routinely demand a 4-point inspection covering the roof, plumbing, HVAC, and electrical.
And if the inspector opens the panel and sees an FPE logo, the insurance company just walks away.
Very often, yes.
Yeah.
They will refuse to bind coverage entirely, or they'll give you 30 days to replace the panel before they drop you. The risk of a total loss fire is mathematically unacceptable to them. However, if you upgrade to a modern, code-compliant 200 amp panel, the statistical risk of an electrical fire plummets.
Which can qualify you for reductions in your premium.
Exactly.
So you are eliminating a massive financial liability. And I assume this plays out in real estate transactions too.
Immensely. If you go to sell a home, an outdated 100 amp panel or a Zinsco box is a giant red flag for a buyer's inspector.
Sure.
It signals to the buyer that the home has hidden infrastructure debt.
Right.
A brand new 200 amp panel proves the home is modernized and assures the buyer they won't be hit with a surprise $5,000 electrician bill the month they move in.
It's essentially unblocking the house for modern living. Constantine's guide goes into detail about how many modern renovations are impossible without stable power. I never realized how much an old panel limits basic upgrades like indoor lighting.
Oh yeah, high-efficiency LEDs are a perfect example. They run on very precise microelectronics. They require perfectly stable voltage. If you wire a house full of expensive automated LED dimmers into a struggling 100 amp panel, the voltage fluctuations we discussed earlier will cause the LEDs to constantly flicker.
Oh, that's annoying.
And the unstable power will quickly burn out those expensive dimmer switches.
Not to mention outdoor lighting, landscape floods, hot tubs, or security cameras.
Right. Every single one of those additions requires a dedicated circuit. You can't just keep piggybacking new wires onto old breakers.
Because that's how you cause an overload.
Exactly. A 200 amp panel gives you the physical slots to snap in new breakers and the total underlying capacity to run them safely. It buys you the headroom to actually live in the modern era.
Which brings up a very strict warning from the sources. If you are tempted to save money by having an unlicensed handyman try to squeeze one more circuit into a full panel, don't.
Please don't.
If an unlicensed, unpermitted modification causes a fire, your insurance company can completely void your policy.
Oh, yeah.
You are left with a burned-down house and zero payout.
The liability of DIY electrical work is catastrophic. This is not swapping out a kitchen faucet.
Which perfectly transitions us to the actual process of upgrading. Because reading through the professional procedure in John Constantine's guide, this isn't a quick parts swap. It sounds more like performing a heart transplant on your house while simultaneously negotiating with the city government and the local power company.
It is a highly choreographed, high-stakes operation.
Yeah.
A skilled crew can typically execute a residential panel replacement in a single day, minimizing how long your freezer is without power. But the actual work begins days or weeks before they ever touch a wire.
It starts with a load calculation, which initially sounded like a boring math test to me, but it's actually incredibly bespoke.
The load calculation is the most vital proactive step. A licensed electrician doesn't just guess that you need 200 amps. They perform a complex mathematical formula governed by the National Electrical Code.
Oh, wow.
Yeah, they calculate the square footage of the home, factor in continuous loads versus non-continuous loads.
Because you rarely run every appliance simultaneously.
Exactly. And crucially, they ask about your future.
Right. They want to know if you're buying an electric vehicle next year or putting an addition on the back of the house. They're essentially building a customized electrical profile for the specific way your family lives.
Yes. Once they calculate your true demand and lock in the specifications, the physical surgery begins.
Okay.
On the day of the upgrade, they coordinate with your local utility company to pull the meter out of the socket. This physically severs the main power feed to the house.
The moment the house flatlines in the operating room.
Yes. The home is completely dead. Then they carefully gut the old panel housing. Now, a very common fear homeowners have is that upgrading the panel means tearing open every wall in the house to replace all the wiring.
Oh, yeah. That was my immediate fear. That sounds like a $100,000 nightmare.
Fortunately, in the vast majority of cases, the existing branch wires running through your walls are perfectly fine and can be reused.
Oh, that's a relief.
Yeah, they are simply rerouted and connected to the new modern breakers. However, the electrician will inspect those wire ends microscopically.
Right.
If they find that chronic heat has scorched the insulation, or if they discover obsolete materials like 1970s single-strand aluminum wiring.
Which is a huge fire hazard on its own.
Very much so. If they find that, they will mandate targeted replacements for those specific circuits.
Because there's zero logic in installing a state-of-the-art 200-amp panel only to bolt it directly to a melted wire hiding in your drywall.
Precisely. During the installation, they also overhaul the grounding and bonding systems. This is an often overlooked safety feature.
Okay.
Grounding involves driving heavy copper rods deep into the earth outside your home and bonding them to the panel.
I've always wondered how that works. Why does the panel need to be attached to the literal dirt outside?
Because electricity is incredibly lazy, it always seeks the path of least resistance back to the earth.
Oh, I see.
If lightning strikes near your house, or a massive utility surge hits your lines, that energy wants to go into the ground. If you don't have a dedicated heavy-duty copper path leading to the dirt, that lightning will find a different path.
Usually through your television, your computer, or worst of all, through you.
Sadly, yes. Proper grounding provides a massive highway for that dangerous energy to safely exit the home.
So the new box is on the wall, the wires are inspected and connected, the system is grounded to the earth, they plug the meter back in. I assume they don't just pack up their tools and drive away at that point.
Far from it. The testing phase is meticulous. They verify voltage levels across both legs of the power feed to ensure perfect balance.
Okay.
They test every single breaker to guarantee it trips and resets mechanically.
Okay.
They meticulously label the panel so you know exactly which switch controls the upstairs bathroom versus the microwave. And finally, they coordinate with an independent municipal inspector.
The city has to sign off on it.
Yes. The inspector verifies that every wire gauge, every torque setting on the breaker screws, and every grounding clamp complies strictly with local building codes.
Right.
It establishes a completely documented, legally sound, and fundamentally safe foundation for the home.
It is an incredibly comprehensive journey. I mean, let's take a step back and look at the sheer scale of what we've unpacked today.
Yeah.
We started by understanding the fundamental physics of why a 60-amp panel simply cannot handle the amperage volume of a 2026 digital lifestyle without creating massive friction and heat.
Right.
We uncovered the terrifying historical legacy of brands like Federal Pacific Electric and Zinsco, where breakers failed to trip or literally arc-weld themselves to the bus bar.
And we learn how to actively read our homes for distress signals. Understanding that flickering lights mean voltage drop and acrid smells mean melting insulation.
And we reframed that ugly metal box from a boring utility into a financial lever that dictates insurance premiums, property values, and your ability to confidently upgrade your lifestyle with EV chargers and high-end lighting. It all culminates in a highly choreographed one-day heart transplant that completely revitalizes the safety of your home.
It really is a remarkable leap forward in residential safety. But synthesizing all these sources about load calculations and modern power demands left me with a much broader, slightly provocative question about the future.
Oh, where are we heading next?
Well, the sources, especially regarding heavy ups, heavily emphasize this massive push toward 200 amp or even 400 amp commercial grade panels, specifically to support heavy modern appliances and electric vehicle chargers.
Yeah.
But we are simultaneously entering an era of bidirectional charging, where your electric truck can actually push immense power back into your house during a grid outage.
Oh, no, right.
Add in residential solar panels and localized home battery storage walls.
Right. Homes are no longer just consuming power, they are actively generating and storing it.
Exactly. So here is the question to ponder. As homes become hyper-electrified, capable of both drawing massive energy and generating it, will the traditional concept of a single centralized electrical panel eventually become entirely obsolete?
Oh, man.
Are we moving toward a near future where our homes function as decentralized, AI-driven microgrids?
What would that even look like?
Imagine a house that dynamically negotiates its own power loads, circuit by circuit, in real time,
Wow.
where the house itself decides, without human intervention, whether it's most efficient at 2 p.m. to pull power from the utility grid, draw from the solar panels, or siphon a little bit of energy from the car sitting in the driveway to run the air conditioning.
Wow. We just went from a dangerously melting Zinsco box in a 1970s garage to an AI-driven, self-balancing home microgrid. That is a staggering leap.
Yeah, it really is.
But given the sheer velocity of the technology we're adopting, it feels not just possible, but inevitable. It definitely makes you look at that gray metal box with a whole new level of respect and, well, suspicion. The next time you walk past your garage wall, I highly encourage you to stop, take a good hard look, and ask yourself exactly what kind of traffic jam might be happening behind that little metal door. Thank you all for joining us on this deep dive into the hidden power grids of our homes. Keep questioning, keep learning, and we'll catch you on the next one.